Hello, and thank you for attending this webinar on how to improve performance with Amazon Athena. My name is Scott, and I'm a product manager here on the Amazon Athena team. In this tech talk, we'll cover some of the latest updates for Amazon Athena that will help you improve the performance of your analytics workloads. We'll explore how Athena's enhancements in areas such as joins, nested structures, and subqueries give you better out-of-the-box performance and share tips on how to improve your queries. We'll also dive deeper into how you can control costs as well. Let me kick off today's session by sharing a few quick things about the service so we're all on the same page. Athena is a serverless analytics query service that makes it easy for you to analyze the data in your data lake. With Athena, it's easy to get started. Simply point us to your S3 files, define a schema, and start querying. There's no data loading and no ETL to perform. Athena is cost effective, so you only pay for the data you scan. It's $5 per terabyte scanned in most regions, and you can save money with compression and data partitioning. Athena is also easy to use. There are no servers to purchase, no clusters to configure, and we manage the compute infrastructure for you so you can focus on analyzing your data. And finally, Athena is built on open standards. We're ANSI SQL compliant for querying and support open file formats like Parquet, ORC, and Avro. Our engine is based on open source technologies like Presto and Hive, but as you'll see in today's session, we take open source much further. We launched a few years ago at reInvent 2016, and we're grateful that today we've got many customers, from startups to large enterprises, who've chosen Athena for analytics workloads spanning many use cases, including anti-money laundering, security incident analysis, healthcare and patient insights, and customer analytics, to name a few. Okay, so with a little context set, let's dig into the topic of today's session, which is scale and performance with Amazon Athena. Let's start with the headline. Athena engineers have been working diligently to improve performance over the last year, and we're happy to announce that we've improved overall query performance by over threefold as measured in the 3 terabyte TPCDS benchmark. The threefold improvement was measured for the total runtime, but 25% of the queries saw above a fourfold improvement, and some even as high as 16-fold. And since our price per terabyte remains the same, you're getting all of these improvements at no additional cost, giving you a dramatic increase in the price to performance ratio. The TPCDS benchmark is quite comprehensive, so it's clear that our improvements address an equally comprehensive set of query functionality. To illustrate the point, we pulled the top 10 most improved queries just to give you an idea of the magnitude of those improvements. You can see here that all of these queries were above 6x and several were above 10x. Performance is a fairly broad topic, so for today's session, we will focus on a few areas where we've made improvements in the product over the last 12 months to leave you with practical takeaways that you can implement in your queries and, in the case of new engine improvements, get a better understanding of those improvements and the changes in the system. We'll start with partitioning, which is something that our most successful customers use heavily. Joins were a major focus area for us in 2021, and we've made a host of changes improved logic for join ordering. And we've improved functions as well, with improvements to more efficient behavior on querying nested data, enhancements to window functions, and better order by performance. Rounding out the agenda for today is cost and visibility, which are really important as you scale. We have some recent announcements on compression that will help reduce cost, how you can look under the hood to audit Athena's query plans, and we'll also dive into how you can monitor concurrency with new CloudWatch metrics for concurrency. What I want to emphasize before we go further is that we're constantly working to improve Athena to give better performance and reduce cost. Most of the improvements we'll talk about today were achieved without requiring changes in the data or SQL queries. This means that as an Athena customer, you are already likely benefiting from these and hundreds of other internal optimizations to bring you faster query results on larger and larger data sets. So let's dive into some of those improvements. Our first deep dive for today is partitioning. Partitioning is a very beneficial approach to dividing data into commonly accessed segments that make it easier for Athena to find and process data. Customers using partitioning pay significantly less to use Athena and get significantly better performance. We recommend partitioning as a best practice to reduce data scanned and query processing time. A challenge that arises with partitioning is that it's easy to end up with highly partitioned data as your datasets grow. Take, for example, the logs here. A reasonable approach would be to partition the log data by region, year, month, and day, and hour. However, after some period of time, say 10 years, you'll end up with 1.75 million partitions. This is important because when Athena processes a query, it first makes a call to Glue's getPartitions API before performing partition pruning. If your table has a large number of partitions, this can significantly slow down the query planning phase. The initial solution we provided for this challenge was partition projections, a mechanism to calculate partition values and locations from a configuration file rather than reading them from the catalog on demand. This has been effective for many of our customers, but is a specific implementation to Athena, and it can't be used with other products like Redshift Spectrum or Amazon EMR. For those of you who require a more interoperable solution, I'm happy to report that Athena now supports Glue partition indexes. And for those of you who are not familiar with partition indexes, this is a feature of the Glue data catalog that lets you specify subsets of table partition keys that Glue uses to filter out partitions based on the predicates in your query. Depending on the indices you specify, this can significantly reduce the amount of metadata transferred, as fewer partitions will be returned to Athena to process. The result is faster queries for your highly partitioned tables. Just a quick anecdote on the results. We have one customer with a table with several million partitions who had queries go from 2 to 3 minutes down to 30 seconds after implementing partition indexing. This gave them about a 5x improvement in performance. Obviously, your mileage may vary based on your choice of indices, but the potential should be very clear. The last point to note here is that these indices are not just good for Athena. They work across engines, so they can also benefit your EMR, Glue ETL, and Redshift Spectrum queries as well. Let's take a look at partition indexing in action. Here we have a sample query over a highly partitioned dataset. The dataset is extremely partitioned, having almost 370,000 partitions that span years, months, days, and hours. In this example, the underlying table does not have a partition indexing enabled, and when running it with Athena, it took 45 seconds. After enabling partition indexing, the same query runs more than 30 times faster, taking only 1.3 seconds. Quite an impressive speedup for not a lot of work. What's more, this is a really easy to take advantage of feature. All you need to do is access the AWS Glue console or API, select your table, specify the columns to index, and then enable filtering for that table. Once you've done that, you can flip back to the Athena console and run your query against the table, and you should see a performance speedup. Partition indexing deals with accelerating partition retrieval. Here, we'll focus on how Athena uses the partitions to speed up your queries after partition metadata has been retrieved. One of Athena's features is dynamic filtering and partition pruning. It improves query runtime and reduces data scanned for queries with joins and selective filter clauses for the table on the right side of the join. In this query, we have a large table and a small table, and you can see the query has a very selective filter value in the where clause. After the selective filter is applied to the small table, a value list for the joined column is extracted and is pushed down to the joined table, which is in this case large table, as a filter. This filters out unnecessary rows and partitions from the large table and results in reading fewer rows and partitions from the large table, which reduces query runtime. What's most impressive is that Athena performs this filtering logic automatically and behind the scenes. To take advantage, you don't need to modify your SQL queries or dataset. You just need to have a filter on one of the tables used in the join. Joining data from multiple tables is a common occurrence when analyzing data. So let's dig into some performance tuning tips dealing with joins. Your choice of join order and join algorithm can impact query performance as it affects how much data is read from a particular table, how much data is transferred over the network, and how much memory is needed to build a hash table to facilitate the join. In the last example, which we've simplified and are showing here on the left side of the screen, we had our larger table on the left side of the join and our smaller table on the right. This SQL pattern of placing the largest table on the left side of the join is something we recommend. Athena distributes the table on the right to worker nodes and then streams the table on the left to facilitate the join. If the table on the right is smaller, then there is less memory used and the query runs faster. There are some scenarios in which Athena can reorder complex joins for you. One of those scenarios is where a small, unpartitioned table is joined in a query. For example, consider the following query which joins 3 tables. Here, the syntactical join order is A, join B, join C. With Athena's optimization rules, if Athena considers table A to be a small table, Athena will place table A on the build side of the join and make the join a broadcast join in order to speed up the query and reduce memory consumption. The way it works is Athena will read the metadata of your S3 files and use that metadata to make a determination about the proper place to place the table in order to reduce the size of intermediate query results. Athena's join reordering seeks to minimize intermediate result size, reducing the amount of data transition among query stages in order to speed up overall query runtime. As stated on the previous slide, we still do recommend taking time to place your largest tables on the leftmost side of the join. The behavior described here is specific to a scenario where one of the tables is small and unpartitioned. We'll be working in the future to expand logic to cover more and more scenarios to take care of that automation for you. These tips on joins really simplify the experience of writing performant SQL queries. Let's switch gears and explore some of the performance enhancements available in Athena's SQL functions and better understand how they work. Let's assume we're working on a select query, which returns a large volume of data, and you are happy with the data that's returned. To reduce runtime, you may find yourself experimenting with different functions to improve the time between query submission and when you see results. When a select query is submitted to Athena, it progresses through various stages of execution, which we reflect in CloudWatch as the running state. After Athena plans the query, Athena reads the source data, executes the query on the data, and then produces a result file. As suggested by this graphic, queries that return a large volume of data can actually spend more time in the result writing stage than the query execution stage. If your goal was to get additional performance out of this query, you may consider using our create table as select, also known as CTAS, or UNLOAD operators to improve the result writing stage of query execution. What makes CTAS and UNLOAD different than the select statement is that Athena parallelizes the result writing stage for CTAS and UNLOAD queries. As shown here in the graphic, the addition of CTAS or UNLOAD can shrink the overall runtime of the query to make data available to you sooner. With CTAS and UNLOAD, you can also choose the output format and compression type. And with CTAS, you can write query results to a table which you can later query through Athena. With UNLOAD, you can write results to a file for consumption by a downstream application. Most users don't have control over the structure of the data they're analyzing and need to make do with what they have. This occurs for a variety of reasons. For example, perhaps another team owns the data or the data was generated by an upstream application. An example of where this can arise is with nested complex data types in Parquet and ORC datasets. Let's take a scenario where we have a product inventory data stored in a Parquet file and need to query some semi-structured product metadata that was added to the inventory dataset over time. Here we're interested in getting the discount field for each product that has a discount associated with it. We see that the discount field is nested inside a struct. In this improvement for Parquet and ORC datasets, when a nested field is queried in a complex data type like a struct, array of structs, or map, only the specific subfield or nested field is read from the source instead of reading the entire row. And if there's a filter on the nested field, Athena will now push down the predicate to the Parquet or ORC file to prune the content at the source. This behavior has led to significant savings in data scans and large reductions in query runtime. With this improvement, you no longer need to flatten your nested data to get improved performance. If you are using rank window functions, it used to be the case that all input data for the rank window function was sent to the window operator for processing, and the limit and filter clauses were applied at a later stage. Here's a good example of where we're trying to get a list of the top 100 retail stores across several regions. Athena can now replace window operators with a top n rank operator, push down the filters, and only keep the top n values, where n is the limit number, entries for each window group. This reduces memory consumption and data transfer, which altogether improve query runtime. With this enhancement, only a small amount of data is kept in memory and sent across the network because the filters and limits are pushed down to the source. This makes the entire workflow more efficient and enables the engine to process a larger amount of data with the same resources. To round out our sample of SQL function enhancements, let's discuss order by. Queries using order by, such as the one on the left, previously performed the order by operation on a single compute node. This behavior was slow and, on occasion, caused queries to fail due to out-of-memory conditions. We added a distributed sorting to scale and stabilize sorts on larger query results. With the addition of distributed sort, queries like this one are now faster. The same query saw more than a 2x speedup without any changes in the SQL code. If you're interested in getting even more performance, we have a bonus tip for you. That tip is to add a limit to your query. If you're only interested in the top n values, adding a limit can speed up your query by quite a bit. Here we see that the addition of a limit caused a speedup of about 100x, bringing our runtime down from 600 seconds down to just 6. Now let's talk about a couple of important aspects of managing Athena, and that's related to cost and visibility. As I mentioned during our intro to the service, Athena makes it easy to get started, which means it's also easy to scale out the number of users and workloads deployed on the service. As scale increases, monitoring and controlling cost becomes an important activity. So here are a few new items we've delivered to help you do just that. Compression has been a proven mechanism for reducing cost, and fewer bytes means fewer bytes scanned. This is particularly useful if you're using delimited text file formats, but is also helpful with more efficient formats like Parquet and ORC, which are common in analytics. The first bit of news is that we've added Z-standard to the list of our supported compression algorithms. Z-standard has demonstrated compression similar to deflate, but with much better speed, especially in decompression. We've observed some teams enjoy up to a 30% reduction in size when moving to Z-standard, so it really does work. Z-standard compression is available for creating and reading tables formatted in ORC, Parquet, and text files. Also new is the ability to write files with bzip2. bzip2 is a bit more compute intensive than other codecs, but is fast and compresses very well. Probably the key aspect of bzip is that it's splittable, meaning you can break up larger files, which allows Athena to parallelize processing and provide better performance. Athena does support a variety of other compression algorithms, including gzip, snappy, LZO, and LZ4 that you can apply according to the data types that you have. Next is news on one of the most requested feature areas for Athena. Last year, we launched the explain statement, which takes in a query and returns the engine's execution plan in JSON, text, or a graph viz visualization format. Execution plans are a popular tool in the database world for tuning and optimizing queries and validating that your changes in your SQL queries are reflected in the plan. Now, while this tool has helped many of you, we heard more and more that you'd like to see additional details of the plan, especially those that can help you understand cost. And to do that, we launched the explain analyze statement. Like explain analyze inputs a statement to create its execution plan, but Athena actually executes the statement so that it can enrich the plan with computational cost data. With Explain Analyze, you can now see the CPU time spent within each plan segment, along with the number of rows of data that were processed. These additional metrics can help you assess the performance profile of your query. And with details on the number of rows processed, you can validate the effectiveness of your query predicates and identify areas to further optimize your query. Administrators can also use the Explain Analyze and the information it contains to determine queries that require governance to control costs. Keep in mind that when using the Explain Analyze function, it does execute your query, so standard Athena charges do apply. One more cost and visibility enhancement for you. To expand visibility, we've added a new CloudWatch usage metric that reports on how your account uses your Athena resources. The new metric we've added is the active query count, and it is the sum of all queued and executing queries within an account. It's broken out by DDL and DML statements, so you have additional granularity for plotting and visualization. The metric is refreshed every minute, giving you a great time series dataset that lends itself nicely to graphing and dashboarding. Besides giving you a continuous look into your usage, you can use the active query count in combination with other metrics, such as data scanned, so you can look for usage patterns and trends that inform your workload planning and cost management efforts. This will help you keep an eye on high and low usage accounts and identify opportunities to optimize your workloads. If you are monitoring usage through CloudWatch, you might have noticed a recent increase in the active query count. That's because we've recently increased our default quota for active DML queries in most regions. In some cases, we've increased the limit by up to 8 times what the limit was before. And we hope that with these increases, you're able to run more workloads on the service than you could before. And as a reminder, if you need additional capacity, remember that you can request increases using the AWS Service Quota console. We covered a lot of topics today, but wanted to leave you with some resources to build on the knowledge gained from today's session. The first is a very popular AWS Big Data blog post, and it focuses on Athena. That's the top 10 performance tuning tips for Amazon Athena. This is a really great resource that I recommend you bookmark, and be sure to check back often because we're often adding or updating our tips with new recommendations on how to get more and more out of Athena. We recently released a second blog, which goes a bit deeper into a few of the internal engine optimizations that we discussed today. And that's the Amazon Athena Engine version 2 Performance Enhancements blog. This blog is really great and has pertinent benchmark data if you'd like to go deeper on performance, especially if you're familiar with the TPCDS benchmark and are interested in seeing how performance has changed over some of those really complex queries. Earlier, we touched on partition indexing. That's an AWS Glue feature that we now support with Athena. We've got a great blog post here which explores this topic further and sets you up with a reproducible example so you can see some of those before and after impact of the partition indexing feature on your queries. Definitely encourage you to try out that blog post and give those queries a try. If you want to go really deep, some final exciting news. We recently released a brand new book focused on Amazon Athena. It's a really great desktop reference manual that offers a wealth of information about the service and how to get the most out of it. That's called Serverless Analytics with Amazon Athena, and you can find it on Amazon.com in paperback and ebook formats. That about wraps up our session for today. Thanks again for your time and for your continued use of Athena. If you have any questions or feedback to share, please reach out to us at athena-feedback@amazon.com. Thank you.